The question we are considering today is as follows. Please pause the video and read the question. Now you will see the figure given in the question. Let's write the assumptions. Steady state conditions prevail. Air has negligible solubility in chloropycrin. There is no chemical reaction between air and chloropycrin. As mentioned in the question, only molecular flux is considered. Entire system is maintained at constant temperature and pressure, that is, C equals P by RT. Both species form ideal gas mixture. As you can see, the flask has two parts, one cylindrical part and one conical part. To do shell balance, it is important that we fix the origin. The origin will be fixed as shown. To do this question, it is important that we split it into two parts. One is the conical part and one is the cylindrical part. First, we will consider the conical part. The first thing we are going to do is to establish a relationship between R and Z. From the figure, when Z is equal to 0, R is equal to 3 cm, and when Z is equal to 5 cm, R is equal to 1 cm. From this, we obtain 2 points, 0, 3 and 5, 1. And we will use the general equation of a line to find the relationship between R and Z. This is how we obtain the relationship. Therefore, the function we obtain is R equals 3 minus 0.4Z, which will be our equation 1. Now we know that input minus output will be equal to 0 considering the conservation of mass, and also because there is no chemical reaction involved. Considering a small portion delta Z of the conical flask, we get ANA at Z minus ANA at Z plus delta Z equals to 0. Now dividing this by delta Z and limiting delta Z to 0, we get the following. This leads us to the fact that the rate ANA is constant, which is equal to NA dot. We know that total flux is equal to molecular flux plus convective flux, which leads to the following. CAVZ is neglected because we are only considering molecular flux. Therefore, Na is equal to minus C dAB dXA by dZ, which is our second equation. As we derived before, we know that dAna by dZ equals to 0. Now we know that area is equal to pi r square. Substituting Na and R in the above equation, we get the following. Now we have to integrate the equation. Note that pi has been removed because it is a constant, and so has minus C dAB. Now at Z equal to 5, we get dXA by dZ equals A1, which is our equation 3. Now integrating dXA by dZ, we get the following. Now in this equation, we are going to substitute the following conditions. At Z equals to 0, which is at the interface, XA is equal to 24 by 760. 24 is the partial pressure of chloropycrin. Partial pressure by total pressure gives us XA. Now at Z equals 5, XA equals XA5. This is what we obtain after substitution. Let's name it equation 4 and equation 5. Now let's consider the cylindrical part. The difference here from the conical part is that cross-sectional area is constant. Now, dAna by dZ equals 0, and since A is a constant, we are removing it. Substituting Na, we get the equation, and now we have to integrate it. Integrating this, we get dXA by dZ equals B1, which is a constant. Now at x equals 5 cm, dXA by dZ equals B1, and that will be our sixth equation. Integrating dXA by dZ, we get XA equals B1Z plus B2, and B2 is the constant of integration. Now to the above equation, we will substitute